Hi people, welcome back to the next and last lesson, I think, in deflection. I took this off page out of the core notes there. I don't know if I said it recently, but all the bits I do, the core notes are there for extra additional reading. And I went to page number 6.11, that means chapter 6, page 11, 6.11, and I took that one out there. There's a cantilever there. It's 4 meters long. It's got a 2 meter UDL of 2 k's per meter. And the question says work out the deflection at that point there and that point there. They call it x1 and x2. And of course y2 is the deflection at x2, which is minus 7.7 millimeters. And of course that will have a bigger deflection. It will be plus, well, it says minus. Well, it should be both minus actually, because they're both falling below the line. Yes, they should actually both be minus, and that will be minus 2.26 millimeters, but that's given in meters there. Okay, so because it's bending down like so, there's a slight deflection, and the biggest deflection will be at x1, which is y1 there. Right, I've drawn it there. So before we can start, we need to calculate the support reaction. So I'm going to do, so there is definitely going to be a VA. VA is going to be like so. So I'm going to call that V. Let's call it A. Okay, VA. And of course, there's definitely going to be a reaction moment like so. Okay, because the B wants to turn this way, the reaction will go the opposite way. Right, so VA, VA is easy, ne? VA, just by inspection, VA will be 2 times 2, which will actually be 4 kilonewtons, and it's going up. I guess it's 4 kilonewtons going up. That's easy. Right, sum of the moments about A is equal to 0. So that's going to be an anti-clockwise reaction moment, okay, plus the one on the beam will be 2 times 2, 2 times 2 times, what's the lever arm? The lever arm goes to the center, so it will be plus 2 times 2 times 3, plus 2, the value of it, times the length of it, times the lever arm, which is equal to 0. So therefore, the moment at A is equal to 12 kilonewton meters. Lekker easy, no? Yes, very easy compared to the previous one. So it's 12 kilonewton meters. Right. And as we said in the past there, we're going to take moments about the right hand end. So X is starting from there and going the other way, like starting there, and there's a X. Okay, right, I'm taking moments on the right hand end, and by the way, E is given as that in the problem there, 2 gigapascals, which is the same as 200,000 Newton per millimeter squared. You should know that by now. And now from there, if I go back to the notes there, if I flick back to the notes, it says there that the beam width and section is that. So what we need to do is go to the steel table and pick out section 356 by 171 by 44.8. And from that there value, I see that Ixx is equal to 121. 121 times 10 to the power 6 millimeters to the 4th. So it's not given, you need to pick it out from steel tables. Right, I'm taking moments about the right hand end of the beam, and I'm gonna set up my bending moment equation in terms of Macaulay. Let me change the color. Right, so I'm gonna say the moment at X can be written as EI. There we know, old stuff, d to y dx squared. Right, I'm taking moments right here. Okay, so at the left hand end there, I have a moment. Can you see that? So I have a moment, so it's 12, but it's an anti-clockwise moment, so it's just minus 12 Ne? At the left hand there, I've got a moment of minus 12 kilonewton meters. Right. Moment with regard to that force there, it will be plus VA times, okay, remember we all distances is in terms of x, so it will be times x, that's it, times x. And the UDL is anti-clockwise with respect to the right hand end of the beam there, so it's minus 2 times, what's the length of it in terms of x, is x minus 2, okay, times half of x minus 2. Remember, the UDL has gone to the end of the beam, so it's 2 times x minus 2 times the distance from there to there. It's half of x minus 2, so therefore it's x minus 2 all squared. Okay, so that's the bending moment equation. Job done. What I need to do next? Integrate that twice. Okay, and of course when I integrate first time, I get the slope equation, which gives me EI dy dx, and it will be minus 12x plus VA times x squared over 2. That's going to cancel, ne? So it's, and don't forget we want square brackets, so it's x, and never keep the brackets always square and never take anything out or multiply it out, so that will be cubed over 3 plus the first constant of integration. Okay, right, I integrate again to get my deflection equation. So it's EIY is minus 12 x squared over 2 plus VA times x cubed over 6 minus x minus 2, keep the bracket square, it will be now to the power of 4 over 12, and of course when you integrate the constant it becomes C1 times x, plus we get a second constant of integration and we call it C2. Right, we need to determine C1, C2, and once we know C1, C2, if we put the value of x in, we can determine y, because we know what E and R is, right? But we're going to do that at their boundaries, along a boundary condition. What do we know? We know that at A there, okay, the deflection, okay, sorry, at A, my apologies, at A, x is equal to 0, and y is also equal to 0, okay, because it's been held in place there. So it's not going anywhere. So at A, x is 0, y is 0. Right, I'm putting all of this into that. So that's going to be 0, that's going to be 0, that's going to be negative, so it's 0, that's going to be 0, that's going to be 0, so therefore naught is equal to C2. So C2 is 0. So our first constant of integration is of C2 is 0. Alright. Now just be careful. What else do we know about the cantilever? Okay, we also know that at the fixed end there, the slope is equal to 0. So at A, at x equal to naught, dy dx is also equal to 0. Okay, because the beam is just straight at that point. Okay, and just by the way, for a fixed end of a cantilever, dy dx is 0 and dy dx is the maximum at the end there. Okay, you think about it. For a cantilever, dy dx at the fixed end is 0 and the slope at the far end is maximum. Okay, I don't know what it is, but you know it's maximum. Right, so I'm going to put this into my slope equation. So dy dx, can make that 0. Okay, I'm putting this in there. So that's all 0 is equal to. Right, that's 0. So that's 0. That's 0. That is That's negative, so it's also going to be 0. So therefore, C1 is also just happens to be equal to 0. Okay. Right, I've just divided my page up a little bit so we can see all at the same time. Right. So from that we found there that C2 is 0, C1 is also 0. Okay. Right, so the question is determine the deflection at x1 and x2. Okay. So at x1, x is equal to 4. So at x, at x1, x is equal to 4. Because I want to work out my slope, I put this in my slope equation. So let's see. So E, I, Y, I'll say at x1. Right. It's 4 there, so that will be minus 12 times 4 squared over 2 times 4 squared over 2. Okay. Plus VA, which is 4. So it will be 4 times x cubed. What's x? X is 4. Okay. Don't confuse yourself with this. That's just a name of a point. Okay. I would call it A, B, and C. No? So if we call that C, it will be at C, x is equal to 4. At B, x is equal to 2. At A, x is equal to 0. Okay, that's, I wouldn't use x1, x2, it just confuses things a bit. Right, so I'm finding the slope at point C, which is x1. Right, so I'm putting all of this into here. So that is VA, which is 4 times x cubed. So it's 4 cubed over 6. Okay. So that will be minus. That will be 4 minus 2. That will be 2 to the power 4 over 12. Okay. That's 0, that's 0. So that's, I'll say, plus 0, just for now. Okay. And let's work it out. See what we get. Stop the video and check that you get the same as me. And you should have gotten minus 54.67. Okay. Minus 54.67. Okay. And of course, now we're going to make y the subject of the formula. So the deflection at x1 is equal to minus 54.67 times the conversion factor. If you forget that, if you leave it out, that's going to be all wrong. Over EI, I'm making that the subject of the formula. E is 200,000 newtons per millimeter squared times 121 times 10 to the power 6. And I get minus, why is it minus? Because it's deflecting down, it's below the 0 line. Minus 2.26 millimeters. Okay. And if I go back to the answers, there we go. X1 is Y1, the deflection at X1. If I multiply that by 1000, I get 2.26 millimeters. So that's correct. Okay. So the deflection at the far end is 2.26 millimeters. The next one there, the question says find the deflection at B. Okay. We do the same thing, but X is equal to 2. Okay. So at B or at X2, X is equal to 2. Do the same thing. See what you get. So I'm going to say at X2 or B. Okay. Or B if we wanted that. X is equal to 2 meters. There we go. And because we want to find the deflection, we put this in the deflection equation. So I'm going to put X equal to 2 in that equation there. Right. So EI. So EIY at X2 is equal to, so that's minus 12 times, that will be 2 squared over 2, 2 squared over 2, plus VA, and what's V? V is 4, so plus 4 times, what's X? X is 2, so it's 2 cubed over 6, 2 cubed over 6. That's going to be 0, so it falls away. That's going to be north, that's going to be north. So it's just that there. Okay. So check what I get. And you should have gotten minus 18.67. So it's minus 18.67. And of course, now we're making y the subject of the formula because we want to find the deflection. So y at x2 is equal to minus 18.67 times the conversion factor over EI, which is 200,000. And I is 121 times 10 to the power 6. And check my answer. You should have gotten minus 0.77 millimeters. And if I flick back to the answer, that's 7.7 millimeters there. Okay, that should actually be a minus there, not a plus. Okay, so people, that is our, notice that cantilever is a bit shorter, not so much work. Okay, but the only essential difference is, remember, when we sum moments there, okay, and if the fixed end is the side here, on the left side, when we sum moments there, do not say minus 12 times x, that will be wrong. That will become minus 12x squared over 2, and that's all be wrong. Okay, we're summing moments, the 12 is already a moment, so we just record it as that, and of course that's force times distance, and that's force times distance. Okay, get the moment formula there, integrate twice, and then put in the values at the boundary conditions. One is, notice there, they're slightly different. At the fixed end, the deflection is 0. At the fixed end, the slope is also 0. And we use that facts to determine C2 and C1. Okay. And then wherever the distance we want to find the slope, put the values into x, into the slope equation, find the values there, and don't forget to multiply by the conversion factor of 10 to the power 12 and divided by EI. And of course, if you need to find the slope somewhere, the conversion factor is times 10 to the power 9. Okay, if we want to find the slope of a point. Okay. Okay, people, that's all I am going to say there on deflection. If I go back to the notes there, oops, that's a bit too fast, didn't I? It went a bit nuts there. 6.10, right? Okay, so on page 6.10, self-evaluation, there's beams there. So work through all the ones I gave you in my handout there, and also work with these ones here, x1, x2. Okay, x1, the corresponding deflection at x1 will be y1, so that means the deflection at x1 there is 0.44 millimeters, and at y2 there it is 0.31 millimeters, or you can leave it as meters, just don't get the units mixed up. Okay, there's the beams, there's the answers. Find the deflection at all the x1s and x2s, and the answers there are given for all of those ones. I just did that one. There's another one there with a pointer at the end there and a UDL over there, and there's another 8 or so to do. Okay, people, do all of them. The answers are there. If you have any questions, send me an email and I'll try and help you with the solution. Okay, people, that's it for now, and I'll see you in the next lesson. I think there should be another lesson coming up.